So what have we done so far in the previous chapter? The previous chapter we have learned about memory management. Okay, how does the operating system handle all the processes in the computer system? Okay, so each process goes through the operating system needs to be processed only by the CPU. And in chapter 8, we learned that how does the operating system handle multiple processes. So we came across something which is called paging and segmentation, and we learned how to calculate the page size, the frame size, the logical address, and the physical address. Okay, that was in chapter 8. In chapter 9, we're going a bit more detail. We are going to cover something which is called virtual memory. Okay, virtual memory. So virtual memory is simply by which in a condition whereby your RAM size in your computer is full. Okay, so the RAM is already full with all of the processes that needs to run. So what the operating system will do is it will take a part of your hard disk and convert that into a physical memory. So if you remember in chapter 8, I always refer to physical memory, and I have always told you physical memory is your RAM. Okay, so in chapter 9, what we are going to do is we are going to understand what is virtual memory. So virtual memory is a condition whereby your RAM size, your physical memory is full with all the processors, but more process needs to come in. So what the operating system will do is it simply will take a portion of the hard disk and convert that into RAM. So let's say your RAM size is, we just give it a number, say 60 megabyte. Okay. So if in a certain condition your RAM size is full, then automatically the operating system will convert part of the hard disk and convert that into physical memory or RAM. So now you have your RAM size will increase. That is what we say as virtual memory. All right. So in this slide here, we are going to learn about, in this chapter, we are going to understand about demand paging, page replacement technique, and allocation of frames and trashing. Demand paging is a condition, it's almost similar in chapter 8 where we have frame size and page size and logical address and physical address. But in chapter 9, when we say demand paging, okay, when we say demand paging, it simply means that the files or the process files that was previously inside the RAM, yes, it's also inside the RAM, but in this chapter, in demand paging, these files are inside the RAM, but it's inside the virtual memory. It's inside the virtual memory. Okay, so where is the virtual memory? The virtual memory is inside your hard disk actually. So virtual memory is simply the operating system taking a part of the hard disk and converting that into your physical memory or your RAM. So how do we do it in Windows, for example? If you go into your system properties, and you click on advanced, you can see virtual memory here, and you can change the size of it. So it is also giving you a description of what virtual memory is. It's a paging file. It's a paging file. It's an area on the hard disk that Windows uses as if it were RAM. It explains clearly. So what it does is it takes a portion size, in this case here, 13671 megabytes of the hard disk and converts that into RAM. That's it. So when the operating system converts that space into RAM, that space now is now referred to as virtual memory. So we can actually change what the size of the virtual memory. So by default, this is what Windows gives you. So you can check in your own PC. You just go into System Properties, Advanced, and then you can see the settings of virtual memory here. You can decrease it, you can increase it, not a problem. It will not affect, if you increase it to a bigger size, it's okay. If you reduce it to a smaller size, it's still okay. However, if there were conditions that there are more than one process or there are your RAM size is full, then it might affect the performance of your computer system overall. Okay. All right. So this is how it looks like. Okay. So the objectives of this chapter is you want to look at the benefits. What is the benefit of virtual memory? So obviously the benefit, the simplest benefit that you can imagine is you get a bigger RAM size. So RAM size you dah kecil, now you add on more RAM. So now you have, obviously you will have a bigger RAM size. And then we are also going to understand demand paging. What is page? We understood what was paging in chapter 8, how to calculate physical memory, logical memory, page size and frame size. But in virtual memory, it's still similar, but on a different level. And we are also going to see the principle of working set, and we are also going to look at shared memory and memory map files. Okay, so a little bit of the background before we jump into what is demand paging. Code needs to be in memory to execute. I think we understand this. Okay, each code that needs to be executed needs to be in the memory. Okay, it needs to be in the memory. However, sometimes these codes are never being utilized. For example, let's say I'm using now, I'm having a program called Microsoft Word, Microsoft PowerPoint. So this is the process which is running, which is executing at this point of time. So where are these files? Where is this Microsoft PowerPoint files? So these PowerPoint process files are all inside the main memory or your RAM. Okay. So some files are being utilized, some files are not being utilized. It depends on what are you doing inside what functions are you doing inside Microsoft PowerPoint. Okay, so the statement here, not entire program are rarely used. Okay, so entire program code not needed at the same time. So there are some codes which are not needed, but they are also here. They are also already inside the uh, physical memory. So if these codes are here, and another code which is really another process which is really necessary to be included, so this means that there are some codes which are not necessary, which is inside the RAM. Other codes which are necessary, it's not inside the RAM. So this is why the operating system creates something which is called virtual memory. Okay, so it only loads partially loads program, partially loaded program. It only loads what is necessary. What is not necessary, it pushes down to your virtual memory. Okay, all right. So by doing this, you will increase your CPU utilization. So you will increase. That means other process which needs to be run, which needs to be executed, can run easily because it's now inside the RAM. Okay, and less input output is needed. So because we have to switch, because the operating system is switching between processes, so less of this is now being done. Okay, so basically this is how it looks like. So virtual memory separation of logical memory, CPU and RAM, from physical memory. Okay, so this is basically it. So you have your RAM size here, you have your CPU here, and you have your cache memory in between. All right. So cache memory is not part of the RAM, it's actually inside the CPU. Okay, so here is where you increase your virtual memory, or you implement your virtual memory. It is part of the hard disk over here. So this green and red is actually the same thing, which is your RAM or your physical memory. So what the operating system is doing is simply by increasing the RAM size by taking some space from the hard disk and making that into RAM or physical memory. Okay, so basically this is what we have. Okay, so when you implement virtual memory, you can be doing it through demand paging or demand segmentation. What does this mean? This means each program will be either divided into several pages like we did yesterday, or several segments like we did also in chapter 8. Okay, the only difference between chapter 8 and chapter 9 is we call it demand paging. Okay, so and demand segmentation. In paging and segmentation in chapter 8, there is no concept of virtual memory. That means all of the pages, all of the segments are only inside the physical memory or your RAM. In chapter 9, when we implement demand paging and demand segmentation, the pages are not only in your physical memory or RAM, but also inside the virtual memory. Okay, so when you see the word demand paging or demand segmentation, then we are actually talking about the pages or the segmentation which is inside the virtual memory, as compared to the chapter 8 where we have demand, we have paging and segmentation. There is no demand there, so those pages or those segments are all inside the physical memory only. There is no utilization of the virtual memory. All right. So basically, it looks like this. You have your CPU here, and you have something now. We have something new here. We have the memory management unit (MMU), and we have a relocation register, and it points to a physical address. Bear with me. This relocation register is a hardware. Okay, so it has a register here. Now, what's the difference between between what we learned yesterday and today? Yesterday we had something called the page table. Okay, so in demand paging we also have the page table, but we also have something which is called the relocation register. This relocation register refers to, it only appears and it refers to virtual memory. So whatever address which comes out of the CPU, because the CPU does not know where the file is it inside the physical memory or is it inside the virtual memory? It simply comes up with an address. So the relocation register will do some calculation. In this case, it's just 2000 plus 324, and you will get a new physical memory, a physical address to locate where is the file inside virtual memory. Okay, so in demand paging, we start talking about the pages and segmentation inside the virtual memory. In paging or in segmentation in chapter 8, there is no use of virtual memory and no use of relocation register. Okay, so this is how it looks like in demand paging. Similar, we have the logical address, we still have the page table, we still have the memory, and we have the hard disk over here. However, as you see here, I put a big red box here. So this big red box refers to as virtual memory. So virtual memory, VM. Okay. So this is the original RAM size, and these are the additional RAM size given to the process. Okay. So let's look at this example. In page 0 is inside frame number 3 and it's valid. Okay. And in page 2 it's inside frame number 5 and it's valid. Page 4 is inside page number 7 and it's number 7 and it's valid. This invalid means it's either, okay, there are two conditions here. The page and the frame is not inside the physical memory but is inside the hard disk or is inside the virtual memory. It's there but it's inside the virtual memory. It's not in the original setting of the RAM. Okay, original. So that's why I made the red box here. All of everything inside this red box is actually the virtual memory. Only the only difference is physical memory is the actual RAM size, and the pink box here is the pink cylinder here is the virtual memory, which is the hard disk, which is also now acting as if it was a physical memory. Okay, so the same thing goes for segmentation. Okay, the pages, the process is divided to several segments, and if you remember, we have the limit and the base. Okay, the base is the starting address and the limit is the how big the file is. So we have segment 0 is inside base number 1400 and the limit is 1000 over here. Okay, this again is also part of the virtual memory. Okay, so in demand paging, let's go into demand paging. Okay, so this is the main memory. Let's focus only on the section of main memory and also the hard disk. So this whole thing here is the virtual memory. Semua ni is virtual memory. So ada files yang akan duduk dalam ni, ada files yang akan duduk dalam hard disk kat sini. So whenever needed, baru dibawa ke the actual main memory location. But it's all inside the virtual memory. Okay. So point number 2, only bring a page into memory only when it's needed. So the pages are brought into the actual main memory only when it's needed. Okay, only when it's needed. Tapi it's still inside the virtual memory. It's there. Cuma we only bring it when necessary only. Okay, so we have something which is called the swapper here. Okay, swapper. So the swapper is a software program under the operating system which actually swaps in which process that needs to be brought into the actual memory and which process needs to be pushed back into the virtual memory. Kenapa kita nak push back? Why do we need to push it back to the virtual memory? Simply because the process or the files are not being utilized at this moment, but it's needed. Diperlukan, but it's not being utilized at this moment. So we push it back first. Biar process lain ambil location. Okay, but it's all inside the virtual memory. It's not inside the hard disk now. We're not talking about the hard disk. It's still there inside the virtual memory. So when it's needed, the swap balik. Why is it not inside the hard disk? If the files were inside the hard disk, then that means the process has already been terminated. But now it's still inside virtual memory. So you have to understand, virtual memory is part of the RAM juga. Cuma it's not being utilized. The files are not being utilized just yet. Bila diperlukan, only then it goes inside the main memory. Okay, so now we have the basic concepts. Okay, so now we have something which is called the valid invalid bit. So the valid invalid bit inside the page table refers to if it's valid, bermaksud frame tu ada dalam main memory. Okay, so it's valid, it means this frame is valid, so the files is inside physical memory. Okay, it's there. Okay, and it's also here. Kenapa ada kat sini pun? Yes, betul, dia ada kat sini. But these are, so you have to understand, proses A ni file dia besar, so only dia akan bawa what is necessary. Yang baki lagi tu disimpan dalam virtual memory. Again, this whole thing ni is the virtual memory. So yang in this case ni, page 1 here, but is invalid. Why is it invalid? Invalid means it's not inside the physical memory, tetapi it's inside the virtual memory. It's there. It's here. So when it's needed, dia akan bawa ke sini. Okay, dia akan bawa to this location and dia akan update the page table. Page 5 in frame 9. Okay, valid. Oh, valid means it's inside the physical memory. Okay, so all of these are invalid. Why is it invalid? Because it's not inside the physical memory, but it's inside the virtual memory. It's not inside your hard disk. Yes, virtual memory too is your hard disk, tapi it's not being utilized just yet. Okay, it's not being utilized just yet. Okay, it's there, but it's not inside your hard disk. Okay, it's not inside your hard disk. It's like, just imagine, I'll give you another example, simple example. You're driving your car, okay, your car is moving, you're on your signal, everything is on, okay, but let's say you come to your touch and go toll, okay, so what do? Let's assume you don't have RFID and things like that. You open your glove compartment, you open your dashboard too, you take your touch and go, you use it. So the touch and go is what we say as invalid, but it's still inside the car, but it's invalid sebab you're not utilizing it. Only when you utilize, you buka, you ambil, you pakai, and then it goes back to invalid. Okay, it go back to invalid. But the touch and go can also be valid. Where in what situation? Whereby, let's say you use your smart tag, okay, you put your card over the screen, so it's already there, it's already part of the system, it's already part of the car. Tapi kalau you letak dalam dashboard tu, dalam your glove compartment tu, okay, that means you're not being utilized yet. Bila diperlukan, baru you keluarkan, touch, and then you masuk balik. Bila you perlukan, touch, masuk balik. Okay. Kalau spot tag is already there, it's already part of that. That means you're going to use it all the time. Okay. Tapi kalau you masukkan dalam tu, okay, it's there. Only when you use it, you keluarkan. Only when you use it, you keluarkan. Okay, that's how we see paging. Okay, so sometimes we also get page fault. Page fault ialah a situation whereby the page is not inside the physical memory. Okay, or the operating system or the not operating system, the CPU is trying to access a particular frame, tapi frame tu tak ada a page, tapi page tu tak ada dalam physical memory. It's inside the virtual memory. So it has to get that file. So it goes into a fault first. So let's look at this. First, it will load, let's say you want this CPU, this is CPU. CPU nak process a file called M. So it needs to load this program. Okay. So dia akan check dengan, okay, dia akan hantar satu logical address to page table. Tak ada file tu. It's invalid. So it creates a trap. So dia beritahu OS, tak ada lah file tu. Where is the file? Oh, the file is inside the backing store or inside the hard disk. Ada file tu, tapi belum masuk lagi. Ada. So the operating system will get that particular file and bring it back inside the physical memory. Okay, and locate kat mana-mana, and then dia akan update balik the page table and obviously start balik instruction to and then load the file inside back to the CPU. Okay, so the file, why? First, it released a trap, error lah, tak ada. Tapi file tu ada. Where is the file? It's inside the virtual memory, it's inside here. So masuk balik kat sini, and then restart the table, and then only it becomes valid. Daripada invalid, it now becomes a valid file. Okay. Okay. So we are also looking at page replacement technique. Okay, page replacement technique is whereby the page table is full, and which page or which page number you can replace. Kadang-kadang inside the page table is full, page table tu penuh. So where you nak replace? Okay, the frames are full. Kat mana you nak masukkan tu? Because there are some pages which is necessary, some pages which are not necessary. So where are you going to put it? So the operating system will have an algorithm to check. Daripada page ni, daripada dia tengok dalam main memory, physical memory, dia akan tengok page mana yang selalu tak guna. Okay, dia akan masukkan kat situ. So dia akan keluarkan file tu, letak balik dalam virtual memory dan masukkan page baru. So this is what we say as a page replacement technique. Okay, so they use a modified bit. A modified bit ialah untuk test if the page tu selalu dipakai atau selalu tak dipakai. Example, let's say your physical memory is full dengan semua ada frame tu. Semua ada file. Ada proses baru masuk. So proses ni nak duduk kat mana? Everything is full. So dia akan check one by one. Which page is less frequently used or akan digunakan or tak pernah digunakan. Example, you come into a class tu 25 orang. Semua seat dah penuh dah. Semua seat dah penuh. Tapi you nak duduk juga. So how does the lecturer determine where are you going to sit? So dia akan check satu-satu student. Okay, student ni dah habis exam ke belum? Student ni akan buat exam dia. Student ni tak pernah buat exam. So siapa yang tak pernah buat, dia akan keluarkan. Okay, you masuk dulu. You pakai meja dulu. Okay, and then ada orang lain masuk. Okay, siapa yang dah siap? Okay, keluarkan balik. Oh, budak ni ada satu lagi soalan je dah buat. Okay, then he can wait. So keluarkan dia, masuk benda baru. Okay, so this is what we say as a page replacement technique. Okay, so we also have something which is called a victim frame. A victim frame is they check one by one frame too, and they look at if this frame or if this page is going to be utilized, bila dia akan guna. Lama lagi ke? Ataupun baru lagi ke? So if it's going to be used later, okay, keluarkan dia dulu. Okay, so this is what we have a page replacement technique. Okay, we have a frame allocation algorithm and we have a page replacement algorithm. Okay, let's look at this. So we have an algorithm which is called the first in, first out. Okay, first in, first out. Okay, So these numbers here refer to as the page. Okay, page number, page 701. These are all pages lah. So this page can be referred to as process lah, process 70 and so on and so forth. Okay, all right. And these are the frames. Okay, these are the frames. So you can so these are actually the physical memory. Okay, so these files over here 701 blah 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 is coming from the virtual memory. So assuming that the frame is empty, so page 7 masuk sini, page 0 masuk sini, page 1 masuk sini. So we are using the technique of first in first out. Page pertama yang masuk ialah page pertama yang akan keluar. Okay, 7 0. Okay, done. 2. Bila 2 dah masuk, tak boleh. Sebab dah penuh. So it will replace 7. Sebab 7 was the first page yang masuk. So it masuk sini. 0 2. Another 0 is coming in. Tak payah because 0 dah ada. So there is no problem. And then, okay, 1 memang ada lah. 3. So 3 akan replace 0. Sebab 0 yang first in tadi. So 7 dah keluar dah. So 0 was the second one. So dia akan replace yang dekat 0 ni. Okay, so 1. 0. So 0 will take in number 1 kat sini. Okay, number 1 kat sini. So that's one become 0. Now 4, pusing balik, dia ambil location number 2. And then 2 will take location number 3. And 3 will take location number 0. So that's why dia hilang. And 0 will go back. Dia ambil balik 4 tadi. And then 2 and 3. And then 3, oh, dah ada 3 kat sini. So tak payah buat apa-apa. 2 pun ada kat sini. And 1 will replace number 2 kat sini. So last tadi tu ialah number 2. Okay, last lah number 2. Okay, that was the first in. And then 3. And then 2. Okay, this one. And then 0 dah ada. 1 dah ada. 7 pusing balik ke atas. And then 1 and 2. 0 masuk dekat 1 and 2. And then 1 will replace the last one here. Okay. So each time it does a replacement, we call it as a page fault. A page fault ialah a condition whereby the page is not there, tapi you buat a replacement there. So each time you buat a replacement is a fault. So berapa jumlah fault? Is 15. Kira, macam mana you kira? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, this is 15 page fault. Okay, so if we change this page to a different sequence, this sequence, katakan macam ni. So you have 3 and you have 3 frames, tapi sequence ni berbeza macam ni. Okay, so you have, okay, then you might get a different answer. Okay, so the theory is if you add more frames, you can actually cause more page faults. So it does not mean that kalau kita tambah frame kat sini, you will finish faster. Tak. It will actually cause more page faults. And you have something which is called Belady's allonomy. Belady's allonomy ialah bermaksud even if we tambah, let's say we change the string, okay, you will get more page fault. Okay, even if we tukar sequence dia macam ni, okay, or add more frames, let's say we add one more frame kat sini, you are actually going to cause more page fault. Okay, so you can read, I want you to read up on this. Okay, I want you to read up on Belady's allonomy. Belady's allonomy means by adding more frames, you are not actually going to finish faster, but you are actually going to finish slower and you are actually going to have more page fault. So objektif kita nak kurangkan page fault. Okay, so next we look at another algorithm which is called the optimal algorithm. Okay, optimal. What is the most optimal algorithm? Okay, so optimal algorithm ialah you are looking at the same page kat sini, but you are looking page ni akan digunakan bila? Lama lagi tak? Is it going to be used in the next cycle? Atau lama lagi, ujung tu baru nak guna. So we start with 7, 0, 1. Next 2. 2 ni nak masuk dekat 7, 0 atau 1. So tengok ke depan. Ke depan. Lepas 2 ni ialah 0. Oh, lepas ni dia nak guna 0. Lepas tu dia nak guna 3. Lepas tu dia nak guna 0 balik. Lepas ujung ni baru nak guna 1. So 1. Tapi 7 ni baru ujung tu. Paling ujung sekali. Lama lagi nak guna 7. So that's why it replaces with 7. And 0 and 1. Okay, 0 and 1 tu sama lah. Okay, next 0. Okay, 0 dah ada. Okay, now next 3 pula. 3 ni nak replace dengan mana? 2, 0 atau 3. So 0 akan digunakan lepas tu. So 0 tak boleh lah. Okay. 2 pun lepas tu akan guna juga. Tapi 1 ujung ni. Oh, a long time pun baru nak guna 1. So that's why we replace it as about 1, replace it by 3. And then 0 is already here. Okay, next we're going to 4. 4, should it go into 2 or should it go into 2, 0 or 3? Lepas 4 ialah 2. Oh, tak boleh. Lepas ni nak pakai 2. Oh, tak boleh. Lepas tu nak pakai 3. Oh, tak boleh juga. 0 is hujung sikit. Okay, so boleh replace dekat 0 here. Next 2 dah ada kat sini. 3 is here. Now 0. 0, should it go into 2, 4 or 3? Okay, let's look in front. After 0 is 3. So 3 cannot lah. After the 3 is 2. Oh, 2 pun tak boleh. 4 takkan digunakan sampai bila-bila. Okay, so 0 will replace 4. 3, okay, dah ada. 2 dah ada. Now 1. 1 should go into 2, 0 or 3. Okay, tengok ke depan. Lepas 1 ialah 2. Okay, tak boleh. Lepas tu ialah 0. Okay. 3 takkan digunakan sampai bila-bila. Okay. So, masukkan 1 inside number 3. Then we look in front. 0, 1. Okay, 0, 1 is here. Okay, cun. 7. 7 nak replace kat 2, 0 or 1. 0 and 1 lepas tu. So, 2 takkan digunakan sampai bila-bila. So, replace 7 with number 2. So, number of page 4 ialah 1, 2, 3, 4, 7, 8, 9 page. So, this is what we say as the optimal algorithm. The optimal algorithm, we look to the front. In future, bila lagi dia akan digunakan. Okay. And then we also look at, there's also another algorithm which is called the least recently used, yang baru digunakan. Okay. Replace the page that has not been used in the most amount of time. Okay. Right. So we start with 7, 0, 1. Okay, 2. Here. Sebelum 2 ialah 0 and 1. So dia tengok paling hujung saja. Oh, 7 was the last digunakan. Last tu digunakan. Baru guna is 0 and 1. So 0 and 1 tak boleh. So last use. Last ialah 7. Bukannya last sebelah dia. Last yang paling last. Okay. So dia masuk dekat 7. And then 0 dah ada 3. 3 boleh masuk sini, sini, or sini. Okay, tengok ke belakang. Baru digunakan is 0 and 2. So 0 and 2. 1 paling hujung. Okay, so it takes number 1. So 3 will replace number 1 here. And then we have 0. Okay, 0, cantik. 4. 4 masuk dekat 2, 0 or 3. Okay, tengok belakang dia. 0, okay, tak boleh. 3, okay, tak boleh. 2, oh, hujung tadi. So 4 will replace 2 over here. Okay. Next 2. Tengok belakang. 4, oh, baru guna 4. Okay. Then 0, oh, 3 paling hujung. So 3. So 2 will replace 3 here. Next, we have one to replace number 3. 3 masuk sini ke, sini ke, sini. Tengok ke belakang. 2, 4, 0. Okay. So 2 baru guna. And then 4 or 0 paling hujung kali. Okay. So replace dekat 0 here. 3. Okay. And then 0. 0 sebelum dia ialah 3, 2, 4. 3, 2, 4. Oh, 4 paling hujung. So 4. So 0 will replace 4. And then 3 dah ada. 2 dah ada. 1. 1 nak masuk mana? Tengok belakang. 2, 3, 0. 2, 3, 0. 0 paling hujung, so 1 will go inside here. And then 2. Tengok ke belakang. 1, 2, 3. 1, 2, 3. 3 paling hujung. Okay, so replace dekat sini. So 0 replaces 3 here. And then 1. 1 dah ada. Okay, 7. 7 dah replace dengan siapa? Tengok belakang. 1, 0, 2. Okay, 1, 0, 2. Oh, 2 paling hujung sekali. So 7 replaces here. So number of page 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 better than, okay, it's better than first in, first out, tapi lagi teruk daripada optimal. Okay, so our objective is to reduce the number of page fault. So between these three algorithms, least recently used seems to be better, tapi dalam condition ini, lagi better daripada first in, first out, and lagi teruk daripada, okay, lagi teruk daripada, sebab ini baru 9, yang ni 12, yang ni 15. So it's better than first in, first out, lagi teruk daripada ini. Okay, so the best is actually optimal page replacement technique. Okay, I think that's all for today. Okay, trashing you can read on your own. Is just talking about replacement techniques only, and what you have to understand in this chapter is the last three calculation here: first in, first out, optimal algorithm, and least recently. Okay, do you have any questions to ask me?
No, sir.
Okay, all right. So thank you so much for attending my short class today. Make sure you sign your attendance, and I'll see you inshallah in the next class. All right. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Sir.